มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
จะเริ่มได้เลยนะครับ
Okay, good afternoon, everyone, and welcome to East Colloquium online seminar number 3. So organized by the Institute for Fundamental Study, National University, Thailand. My name is Circulate Yu Kong. I am East Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Let me first give you the idea why do we need to do this kind of activity. Most of the time, academic conversation would normally circulate among the scientists, yet bridging the gap between the science world and general audiences is very crucial to for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields come and join in progress of advanced research. For this talk number 3, we are very pleased to have Dr. Maninet Vechakama from Kasetsat University to talk on the topic, the origin of the electrons and positrons. Let me spend a little bit more time to introduce our speaker formally. Dr. Maninet Vechakama completes her bachelor degree in physics from Kasetsat University. Then she went further for her master degree in physics at Mahidol University and PhD in physics at University of Potsdam, Germany. At the moment, she is working as a lecturer at Department of Physics, Faculty of Science, Kasetsat University, Thailand. Her research interests are ranging from, well, correct me if I'm wrong, dark matter, relativistic solar protons, to astrophysics. The talk will be roughly 40 minutes long. Before I stop during the talk, if you have questions, you can put them in the comments. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give this screen to our speaker, Dr. Maninet Vechakama. Okay.
Thank you very much for a very nice introduction. And good afternoon, everyone. Today, I would like to give a talk about the origin of electrons and positrons. Actually, the main purpose of my talk today is to explain what we are doing in our research group called Particle Physics Group at Kasetsat University and called Thailand. So these are the member of our group. So this is me and these are my students. So they are PhD students, master student, and also undergrad. as students. So in this group, what we are doing is something about astroparticle physics. You might wonder what is astroparticle physics. Actually, astroparticle physics is the branch of the particle physics. You can also call it as particle astrophysics too. So this branch study elementary particles of astronomical origin and their relation to astrophysics and cosmology. Basically, you use the astronomical data that they measure, and then you try to explain the origin of elementary particles. For example, like where it's come from, which the origin, like from pulsar, supernova, AGN, or even dark matter, something like that. So these are elementary particles from standard model. You can see that there are quarks, leptons, and also boson. The particles that we are interested are electrons and positron. Electron and positron is also a lepton that have the charge equal to 1. They are particle and antiparticle of each other. So they have spin half, and the mass of electron and positron are equal because they are particle and antiparticle. The mass is about 0.511 MeV per c square. You might wonder why we write the mass in terms of energy over by speed of light square. This is because particle physicists usually think that mass and energy are equivalent according to the equation E equal to mc square. So you can write the mass of particle as E over c square, something like that. But anyway, you should know that the mass of electron and positron are very small compared to the mass of the other particles. Why electrons and positron are so interesting? Origin of electron and positron. Because there are the mysteries of electron and positron. As you can see from these plots, the first plot is about positron fraction. You can see that this plot, the x-axis is the positron energy and y-axis represent the positron fraction. The data are represented in the color dots with the arrow bars. The data are measured by Pamela, Fermi, and the other experiments. The gray area are the astrophysical background. So astrophysical background is the background that we know, or the origin of electron and positron that we know. You can see that in this plot, the area that we know is not cover the peak of positron. You can see that there is a big peak of positron at the high energy that cannot be explained. The same as the spectrum of positron plus electron. This is the flux of electron and positron, and this is the energy. And the same as the other plot, this is the astrophysical background, or the source that we know. So the source, the peak of electron and positron. We call this peak as axis. So there are electron and positron axis that cannot be explained. So if we can explain the electron and positron axis, it might lead to the better understanding of the nature. That's why we are interested in electron and positron origins. So the data that we use in our group the data of electron and positron that measure by all of the experiments that we can use. For example, Damper, Fermi, Pamela, and MS02. Also, the Cherenkov telescope that built on Earth, like Veritas, Magic, and HESS. So we try to use all of the data that public, and we can find the origin of electrons and positron, because these data range in the different energy. So basically, what we are doing, we are searching for the origin of electron and positron by using a different assumption. The first assumption might come from pulsar. So this work has done by me and two of my students. And the other assumption is electron and positron can be created by dark matter particles. So these are done by many students. And the last one is we try to construct the shape of gamma ray distribution in the Milky Way, because gamma ray can be created by electron and positron through synchrotron radiation, or it was Compton scattering. If we understand the shape or the distribution of gamma ray. We can search for the origin of gamma ray and also the origin of electron and positron. Just an example. This work are done by explain the first assumption, which we assume that electrons and positrons can be created by pulsar, and then they travel through the galaxy, and then so this work is organized by Gritapon, Busarakam, and Randon Gan, Kantale, and me. So three of us. The main work is produced by Gritapon and me and Randon. Give her some suggestion. Maybe you wonder what is pulsar. Pulsar is the end of the stellar evolution. If the star have been formed by protostar and then it evolves to be main sequence star. Main sequence star is the star that use the nuclear fusion by hydrogen nuclear fusion, such as the sun. Our sun is in the stage of main sequence star. If the star has the mass between 8 to 25 solar mass, it can evolve to giant star after it use all hydrogen in the core, so it cannot produce the nuclear fission by hydrogen anymore. So the star collapse and then start to use the nuclear fission by helium, and then since helium produce more energy than hydrogen, so it expand to be giant star, and then after that it use the energy from helium fusion, and then the helium run out. They use another products from helium, such as carbon, oxygen, silicon, nitrogen, and so on, until the end they can produce iron. But the problem is you cannot make the nuclear fusion of iron, because iron to get energy then is end. So the lifetime of the star is end. Then the core collapse. When the core collapse, electron and proton combine to be neutron, and then the outer part, the outer layer of the star expand to the space, make the shock wave and the big explosion called supernova. Inside supernova, in the core supernova, you can find a neutron star there. But if the star has mass more than 25 solar mass, it will become black hole, for example. So neutron star is a very small star. It has radius only about 10 kilometers. So since the angular momentum have to be conserved, so the rotation of the neutron star is second. And the magnetic field of neutron star is very strong. If the pole of the magnetic field point to the Earth and then it's rotate, sometimes you got the signal. So the signal become like a pulse, Earth and pulsar. So basically, pulsar is neutron star. When electron and positron created when was electron and positron be created in neutron star? It can be created by the pair creation of the high energy photon in the stage of supernova, for example, and it can be accelerated by the magnetic field and also the shock wave of the pulsar nebula wind, something like that. So and then it can travel through the galaxy and then come to the detector that rotate around the Earth. So our model is based on the assumption that electron and positron can come from pulsar. Electron background from primary electron and positron from supernova, plus electron and positron, which is secondary from the inelastic collision between cosmic ray nuclei and also the interstellar medium. So in our model, the source of the electron and positron come from pulsar, but we also model the background of electron and positron. After the creation, the electron and positron travel through the galaxy. They experience a lot of things, for example, like magnetic field, ion, and also the low energy photon. So they lose the energy very fast by synchrotron radiation, inverse Compton scattering, and also Bremsstrahlung. And then they arrive the detector around the Earth, which in this case we use the data from AMS-02. So from this model, we construct the equation and we calculate and we make the fit function of the pulsar and also the background, and then we can explain where the electron come from, or we can fit the data with our model. If it works, it might be that electron and positron can come from pulsar. We need to explain the propagation of electron that travel from pulsar through the intergalactic medium and then to the AMS-02 or detector that they measure. So the equation of electron and positron is explained by the diffusion loss equation. It looks complicated, and in reality, in our calculation, it's more complicated than this, but I try to explain in the simple way. So this is the equation that explains how many electrons, which energy, gamma or Lorentz factor, can be measured at the position X. For example, this is called electron spectrum. So electron spectrum explains how many electron and positron that you can measure at a position inside the galaxy and with the energy, with the specific energy. Fusion, it depends on how much they lose their energy, and it depends on the source term, how they can be all of the possibility and the good model that we can provide it. So that can explain the spectrum of electron and positron. This is the model, and then we compare the model with the measurement and constrain the model, try to find the parameter in the model that can explain the data, and then we got the result. So this is our result that organized by the positron and electron. Let me explain this plot. What does it means? The x-axis represent energy in GeV, and y-axis represent the flux of positron. This plot is to express the positron spectrum. The red dot with the arrow bars are the data that we measure from AMS-0 we use, and the other lines are our model. So the black line is the model of the background. So we model the background that electron and positron come from supernova and also secondary electron and positron. In this case, it's positron, sorry. And this is the peak of positron that created by pulsar, which is the name of the pulsar is J09545400, something like this. So we use pulsar. We use about 60 pulsar from a catalog called. Sorry, I forgot to mention about the catalog. ATNF, Australian Telescope National Facility, something like that. So we make the fit of 65 pulsar and try to make the best fit that can explain the positron and can also explain the electron spectrum as well. So these are the perfect fit of electron and positron spectrum that we can explain by our model compared to the data that measured by AMS-02. So this work is very successful to explain. So this work have done already. I think this one done, but this one still in the process. So from these two plots, it means that electron and positron can be explained by nearby pulsar, which the distance should not more than 1 kiloparsec years. If the edge more than 3 is the spectrum will be too low and the cutoff will be too fast, something like that. So just would like you to know that the assumption that electron and positron can come from pulsar, it might be work. So because we can fit the data very well with our model. So this is the first work that have done by Dapon, Randon, and me. Is about the origin of electron and positron based on the assumption that electron and positron can be created by dark matter particles. This is the dark matter number 8 work. Is organized by Suvichaya Sethahiran, Chaimongkol Dongjan, Brandon Cantley, and me. So let's see what we are doing. So what is dark matter? Why do we need dark matter? Why do we think that electron and positron should come from dark matter? Basically, there are several cosmological evidence of galaxy, the gravitational lensing, and large-scale structure. So a lot of evidence. If you would like to know what is this, I can explain at the end. So these evidence point out that the universe needs dark matter, and from the analysis of the cosmic microwave background, it was concluded that the total amount of dark matter in the universe is about 26.8%, when the baryon or ordinary matter is only 4.9%, and dark matter is the majority of matter in the universe. So it is possible that dark matter can be the origin of electron and positron. Let me explain a little bit what dark matter properties. Dark matter has to be massive, and there is no electromagnetic interaction. There is no strong interaction, which means there is no color. Color is a spin in the quark models, and there might be weakly interacting. So there is a hope that we can measure property of dark matter particle through the weak interaction, and it has to be very stable, and it's very cold because the structure of the universe, the structure formation needs the non-relativistic particles. So dark matter particles has to move very slow. We call the slow particle as cold particle, something like that. So this weakly interacting massive particle is called WIMPs. WIMPs is the most famous candidate for dark matter particles. Let me explain about our idea. So the idea is, so our model based on the assumption that dark matter particles and dark matter antiparticle can collide and annihilate into electron and positron, maybe also photons. And these electron and positron travel through the galaxy, and then they lost energy by interstellar radiation fields such as the CMB, starlight, and dust emission, interstellar medium such as like ion and so on, and magnetic field. The loss process is the same as the previous work. They are synchrotron radiation, inverse Compton scattering, and also Bremsstrahlung, and also ionization, and also Coulomb collision. So we put all of the possibility in our model. Basically, electron can create from dark matter and then diffuse and loss, and then come to the detector. We use the same model as before. So the data that we use for dark matter study are all of the data that we can that we know. So there are Fermi, MS02, Pamela, Hess, and there are more than these. Also Veritas, Magic, and also Colloquium, which we did not mention in this plot. So these are the data of electron and positron, and also electron plus positron. From this data, we can constrain the property of dark matter particle by assuming that the electron and positron can be created by dark matter. So the idea is, if electron and positron are created by dark matter and travel through the galaxy and lost their energy, the spectrum of electron, when we add the energy loss rate, diffusion process, and so on, we can derive back to the property of dark matter, and we can constrain the property of dark matter particles, such as their mass, their density profile, and their annihilation cross-section. So the model still based on a diffusion loss equation. So this is a spectrum of electron and positron. This is a diffusion. This is the energy loss, and also this is the source term. The important part in this work is the source term. So the other term like diffusion and energy loss, we use the best model that we can find in the literature. But the source term is a term that we can constrain the property of dark matter particles. Let me explain the source term. So the source term is the rate of the electron and positron that can be created from dark matter. It depends on the number density of dark matter times to the number density of dark matter antiparticles, annihilation cross-section, and spectrum of electron and positron, or the number of electron and positron that can be created by one annihilation. So this is the eta is depend on the type of dark matter particles, if it's a Majorana particle or not. So this equation can express in terms of this equation, because the number density of dark matter particles and number density of dark matter antiparticle can be written as the density, mass density of dark matter divided by mass of dark matter particles. So this term become this term. So this one, the spectrum can measure by the detector, and this is the dark matter density profile. It depends on how dark matter distribute in a galaxy. Each galaxy has the different distribution or has different dark matter density profile. And this is mass of dark matter particles, can be a big range of mass, and we don't know what type, what is dark matter particle. This is one property that we have to look for. And this is the factor that depend on the type of dark matter particle, if it's Majorana particle or not. And this is the annihilation cross-section, which is the property of dark matter particles too. And this is a spectrum of electron and positron from dark matter annihilation. This depends on what type of dark matter particle, what channel that it creates electron and positron. In this work, we are consider about 5 channels of leptons and quarks. The leptons channel are electron, muon, and tau. For the quark channel, it is top and bottom channels, for example. So the aim of this work is to constrain the mass of dark matter particles and the annihilation cross-section. This part of the work, we use the density profile as the NFW profile, or Navarro, Frank, and White. The famous profile that can explain the in-body simulation of the universe or the galaxy. Okay, something like that. And then let me conclude again. So we would like to constrain the mass to find what is the mass of dark matter and annihilation cross-section. By using this model, we can let this mass of dark matter particle and annihilation cross-section as a free parameter, and then we can compare our model with the data, and then we fit the model. We let the model not higher than the data, and then we can get something called upper limit of dark matter annihilation. So this is what we get. This is the work that have done by Suvichaya, Setahiran, and me. So this is the plot that tell us about the upper limit of dark matter annihilation cross-section. So this work is about constraining the annihilation of dark matter via cosmic ray, positron, and electrons. Let me explain the plot one by one. So this plot, y-axis represent the mass of dark matter particles, range from 1 GeV to about 10 to the 6 GeV, means about 1,000 TeV. I don't know if it's possible, but yeah, let's see. So this y-axis is annihilation cross-section, sigma time to the relative velocity of dark matter particles and dark matter antiparticle. Basically, when they annihilate, dark matter particle and dark matter antiparticle run together, and then this is the relative velocity. Okay, and each line represents the upper limit from each experiment that measure electron and positron. And each plot represents the different channel. The first one is electron channel. Okay, we explain electron channel first. How can we interpret this plot? we have to understand this line first. This line is called thermal relic cross section. This line estimated by consider the diameter density in this universe. If you know what diameter density in this universe, you can estimate back to the annihilation cross section, because you know that when diameter decoupling in the beginning of the universe, and then when the rest of diameter nowadays is this amount, you can calculate the annihilation rate. So you got the annihilation cross section. The annihilation cross section that fit to the relic. Thermal relic, or the diameter that you can measure nowadays, is 3 times to 10 to the minus 26 cubic centimeter per second. Means if there is diameter or WIMPs, diameter should have these annihilation cross section. It is allowed to have the annihilation cross section higher than thermal relic or higher than this line, but it's not allowed to have the annihilation cross section lower than this line, because if you have annihilation cross section lower than this line, you will create the signal that higher than the signal that you measure. So when you get the upper limit, and the upper limit is lower than this line, you rule out some mass of diameter. So this plot is very exciting, because you can see that there are some lines from some experiments. For example, this line from AMS-02 positron data. This line rule out the mass of diameter that below about 10 GeV. Means this experiment cannot be explained by the mass of diameter that lower than 10 GeV. It's not allowed diameter to have the mass lower than 10 GeV. Diameter have to have the mass higher than that to explain the spectrum of AMS-02, something like that. So we get exciting when the line is lower than the thermal relic. So you can see that these three plots, these three annihilation channels from leptons start from electron, muon, and tau, exclude some mass of diameter particles. The electron channel exclude the mass of muon, but only from the experiment of AMS-02. The other experiment doesn't exclude the mass of diameter particles. For tau channel as well. So for the tau channel, the AMS-02 data of positron also exclude the mass that lower than maybe about 1, 2, 3, 4, 5 GeV, something like that. So this is quite exciting result. But for the lepton channel, we cannot really constrain the mass, because the upper limit is a little bit higher. I mean, we can constrain the mass that each mass should not have the annihilation cross section more than this line or another line. But we cannot the result doesn't exclude any mass of diameter particles. So this is the result from Suvichaya. There are results from Chaimongkol. Chaimongkol also used the data from Cherenkov telescope. It's called Imaging Atmospheric Cherenkov Telescope, or IACT. He used the data from MAGIC, from Veritas, from HES, and HES low energy and HES high energy. So these are the constraints of diameter annihilation cross section compared to the mass of diameter particle that we get for the different channel of annihilation. So the upper limit is still very high compared to the upper limit of the relic upper limit, relic and thermal relic annihilation cross section. Sorry, something like that. So this is the work that done by Chaimongkol and Suvichaya. The work of Chaimongkol and Suvichaya, we did not use any background model, but Brandon Cantale, he used the background model. So he subtract the spectrum of electron and positron with the background. So he remove some of the spectrum. So this result make the upper limit lower. So his result is very exciting because the result exclude a lot of mass of dark matter particles. Look for this one. This one is the data of electron and positron spectrum. So he used the data from several measurements. Actually, the line that connect to each other is from several measurements, maybe MS02 and Colloquium. So these are the different annihilation cross section. You can see that electron and positron channel exclude the mass of dark matter particles very high. This is above 100 GeV. So the mass of dark matter particles have to be higher than 100 GeV if you subtract background. So it just means that the background model has to be improved, and it's very important if we really understand the background of electron and positron, and then we subtract the background that we know. We only have the spectrum that come from the unknown source, then we can assume that it's come from dark matter, and then we can constrain dark matter annihilation. We can get a very interesting result. So this work is very exciting, but we still have to improve the background model, and then we can get the exact upper limit of dark matter annihilation. So these are the work that have done by 3 of my students and me. So about dark matter annihilation. So the next one, okay, we still on the dark matter project B. So this dark matter project is different from the first one because we assume that we have the same assumption that electron and positron are created by dark matter and dark matter antiparticles, but we see the other effect of electron and positron. So the electron and positron are gas. So if electron and positron are at the inner region of the galaxy, it can create gas pressure. This pressure can affect to this is the pressure, this is the formula of the pressure. So the pressure of dark matter or pressure of electron and positron from dark matter annihilation is depend on the spectrum of electron and positron that create from dark matter. I will not go into the detail. Basically, this pressure can affect to the rotation curve of the galaxy. It can push because this effect is pushed out, so it's against the gravitational contraction, so it can affect to the rotation curve of the galaxy. This work I forgot to mention about the name. So this work is done by Chaimongkol Dongjan, Wanchana, and Nakarin and Welwan. So they all have done this work together with my suggestion, and then okay, what they have done is I can skip this. So they consider the different profile of dark matter. You can see this is dark matter halos. In this work, we are interested to compare the effect of 2 different profiles, which is NFW profile. This one, which is a very steep profile, the black one, and the other one is a pseudo isothermal profile. Is the profile that expressed as the core profile. So it's very flat at the inner region of the galaxy. So this is the inner region, and this is the outer region, and this is the density of dark matter. So they compare the effect of these 2 profiles to the rotation curve of the galaxy. They make a lot of calculation of about 15 galaxies with a different model of gas and star in the galaxy. So I will not go into the detail, but they have found out that when we add the pressure of dark matter annihilation in this plot, for examples, like this one express the velocity of the component in the gas, and this is the radius that you measure from the galactic center of the galaxy center. This is the name of the galaxy, so they use different low surface brightness galaxy to study this effect. This is the velocity from the gas. This is the velocity from the disk or stellar or or star, and this is velocity from dark matter. And if you add dark matter pressure, you get these lines, the purple line. Without dark matter, you get the green line. The effect is very small, but it's very important at the inner region. So the dark matter pressure play the important role in the inner region of the galaxy. This is the NFW profile. But for the other profile, like pseudo isothermal profile, the effect of dark matter pressure doesn't play any role because the profile is very flat at the inner region. So I think I a little bit run out of time, so I will go fast. So these are the work that they have done. So this my 4 students have done a very nice work about the rotation curve of galaxy. And the last work is about the tracking origins of gamma rays in the Milky Way galaxy by Fermi Large Area Telescope or SkyMap. So this work is organized by Gan Nunpat and Grit Sawanit and me. So the idea of this work is when you see the emission, such as the gamma ray emission, you can assume that it comes from spherical component and the cylindrical component. So basically, my students try to fit the map by this function. So they assume that the emission or the intensity come from the emission that can express in terms of spherical distribution and cylindrical distribution. This work, this parts have done by the other people, but this one spherical distribution is new that we have added in the model. Let me show the result. This is the raw map in the 3 dimension. We change this map to be this map. You can see that a lot of point source and so on. So they subtract the point source and make the map smooth like this, and they apply the model and then fit the data with the model. You can see that the data is the orange one, and the fit is orange one and the data is the blue one. They fit so well. So basically, 2 of my students can explain the gamma ray distribution by the function that contains spherical and cylindrical distribution, something like this. So these are the parameters that they explain in this plot. So I think I ran out of time. So and these, okay, I don't have to summarize. It's already in my talk. And the other project, we are doing the Fermi analyzing of the Fermi lab data with Amel Shadong Blick in a read with my students Supakit Viveko, and we also have contribution in the CTA paper with lead by Thai CTA group, something like this. So this is Thai CTA group, this is CTA. Okay, then if you are interested in this part, you can ask at the QA part. So thank you very much.
All right. Okay. Thank you very much for a very wonderful talk. Let me ask you some basic, because I don't know much about dark matter, but I believe that this is one of the most mysterious entity in the universe, I guess, right? Because we, at the moment, at the present, we don't really understand what it is and what it's made of, right? That is your work, try to see and try to investigate. Okay, so so your aim is that you mentioned that actually you say the dark matter particles somehow collide each other and produce electron and positron somehow, right? That is it possible to produce some other kind of particles?
Oh yes, they can produce the other kind of particle. They can collide and produce gamma ray directly. It's called prompt emission. It can also gamma ray also produce when electron and positron produce. It's called final state radiation. It's like when it's produced electron and positron, one of electron or positron will feel the other electromagnetic field of the other particles. So it creates a gamma ray. Or it can also produce quarks as well.
Right.
Yeah, top quarks. That's why we have this channel. So you can see this work. We are not only considering electron and positron. We're considering that dark matter can produce muon, tau, top and bottom, and then they decay to be electron and positron at the end, something like that. Because this particle has higher mass, you will not measure them at the detector because before they travel to the Earth, they will decay to be the lower mass of particle. which are electron and positron. That's why we are interested in electron and positrons.
Okay, I see. So there are other possibility, right? That actually they would produce some other kind of particles, actually. Okay, and of course that I believe that this kind of, dark matter cannot, somehow it cannot be explained by the standard model somehow, right? It means that we might expect that the particle that actually made up the dark matter is not in this catalog, right? This your slide here. Right?
Yeah.
It must be something else beyond the standard model, right?
Yeah, we cannot use this amount of elementary or standard model particles, or we call baryons, to explain the amount of dark matter particles at all. Because first of all, we need a lot of dark matter to do a lot of things. For example, you cannot explain the rotation curve of the galaxy by using baryon or standard model particles. When you see the galaxy are rotating, for example, and you measure the light, and you can estimate the mass that come from baryons. The mass of baryon doesn't fit with the rotation curve. This is the curve of the rotation of the velocity that fit to the baryon in this galaxy, and this is the measure curve. So you need a lot of mass here. So, and it's not baryons. The same as gravitational lensing. If you see gravitational lensing, you see that the light bends. So the light is bent by the gravity of the galaxy cluster. You can calculate how it bends, and you can calculate the mass of galaxy. You need about 90% more than the mass that you can see. It's too much to believe that the mass that we see can explain that. And the other thing is about the structure formation. If you would like to reconstruct the structure in the sky, like you see, you made a galaxy map, and then you would like to create the map exactly like that by throw the baryon in your simulation. Baryon never form the structure that you want. You need to throw dark matter or something that very cold and stable in the simulation to get these this structure. And importantly, this one, cosmic microwave background, the anisotropy of the cosmic microwave background need to explain by dark matter and dark energy. So no way to explain dark matter by standard model particles.
All right, okay, I see. So simply speaking, so there are many evidence, direct observed evidence somehow, right? That that actually this dark matter must be something else that actually we are not familiar with, something like that, I would say. So, in this picture is very interesting because from the microwave background map here, and then you get like a pie chart that here, that there is something else also, dark energy. And okay. So it seemed to me that actually, the ordinary matter is just 4.9%, right? This ordinary matter is something that in the standard model, right? That actually we know it well, right? And a part of this that actually is something else that we don't really understand at all, right? Dark matter and dark energy here. Then at this point, I think the universe is very interesting. In itself, because it's made up of something that is like totally understand at all, right? Like dark matter and dark energy, right? Yeah,
it's so dark. Universe is very dark.
That's why it's called dark, right? Because there is dark matter and so dark energy.
It's a dark universe.
Okay, very interesting. Another point is that you have a mathematical model to explain things, right? And it seemed to me that your math model is not really that kind of very difficult to understand. And it's like, I don't know, this is like the model that you build up to try, like, it seemed to me is like the way that the equation that we could have in like a fluid dynamics or something like that. Is that, am I correct? I don't know.
Yeah, you can use this equation for many things that diffuse and loss. So
All right. Okay.
basically, this is nothing about dark matter. I mean, dark matter is only in this one. So
Okay.
basically, this equation is very general. So
All
any
right.
particles that travel in space that lose their energy, diffuse and
I see.
create by something, you can use this equation. So
Right.
when we use dark matter, we only need to change this one source.
Okay.
And
I
when
see.
we use pulsar, we just need to change this one. So
All
this
right.
one
Okay.
is the important term that we will change to explain the source of the positron and electron.
Okay. I see.
Mhm.
I see.
Yeah,
This
the
is
other one, you can explain the particle from the sun with the same equation.
all right. Okay. So this is like common equation to explain that actually
Yes.
the entity like a fluid-like entity, right? That actually it can diffuse or like something like that,
Yeah.
right? Okay.
It's not simple as you see because inside is full of the model that you have to estimate and find the best model. For example, energy loss, you have to consider just an example, you have to consider synchrotron radiation. You have to use the best magnetic model, which we have not found yet.
I see.
Yeah, and the
So-
other one, like inverse Compton scattering, you have to know the distribution of the low energy photons correctly.
all right.
Example.
All right. Okay.
Mhm.
So, well, that's is in some sense this equation somehow hide the complexity of everything in it, right? If you
Yes.
fill it up, so you will get very messy thing, right?
Yeah. For example,
So-
just to solve this equation, you need a green function. Then you have to
right.
assume that in this left-hand side have to be 0. Otherwise, I don't know how can you solve this equation. So you have to assume that it's in the steady state. So the electron and positron have to be propagate very long time until it's
I
steady. Then you
I
can
see.
solve the equation by green function. Otherwise, I don't know the way.
All right. Okay. So it means that somehow you need also the computer to help you to solve the
Oh
equation.
yeah, we
Yeah.
need a lot. We need the computer for sure. We have to write program and run a
Alright,
lot of
okay.
simulation.
And
it's-
what kind of program that you use here?
You can use anything. So my
Right.
students use Mathematica, use
Ah.
Python as they like. You can
Alright,
even
okay.
use Excel, but it might
Alright,
take very long
So
time.
Excel, right? Okay. Excel is so powerful, right? But maybe if you
I'm
if you
not, I'm
good
not
enough.
sure. Just an example.
I don't know. I heard somebody that actually you can do a lot of things with the
Yes.
Excel, but not for me. Definitely, I don't know. I just know just some basic stuff with the Excel. Anyway, interesting. Well, the point is that the point I'm asking you here because I just wonder that actually everything that you did here nothing to do with like a fancy stuff like quantum field theory or it's just, something like that. Not is there something to do with that kind of stuff?
We let that work for particle physicists. So basically, this is the model that they can put in. So this one is the particle physicist work. So this cross-section annihilation and this one eta cross-section annihilation and spectrum. These depend on the particle physics theory that explain how electron and positron create from dark matter annihilation. So it depends on what type of dark matter particles. So particle physicists can work on this, and then we might use their model, for example. Actually, we already work with particle physicists here that when I don't have time to explain because I have too many slides here in these CTA projects. So we work with Ajahn Patipan, Ajahn Chakrit, Ajahn Darit. Then they create the dark matter model, which is called the portal dark matter model, and I don't remember. Yeah, inverse seesaw models. Yeah, I remember. Yeah, then they try to find the sensitivity of CTA to measure that model, for example.
Okay, all right.
But our model doesn't base on our model. The previous work is very independent from the model, so you can leave this one as the independent parameter, or you can use it from. Actually, particle physicist has a recipe for that. Here, it's called Poor Particle Physicist Cookbook. I don't know if you have heard about that.
Well, no, I'm definitely not because I'm not a particle physicist.
Yeah,
But,
it's a cookbook that you can.
Right.
that you can use the spectrum from them. They even provide a Mathematica program that you can create the spectrum when you consider which channel that you want to create a particle from dark matter annihilation or decay.
It's like recipe. Like
Yeah, it's recipe. It's called poor particle physicist cooking because particle physicists are so poor.
right. Very interesting. So, well, can you say something more, a little bit more about your research group at Kasetsart University?
Oh yeah, I thought I say a lot, but okay, I can say more. So
well,
yeah, we
yeah.
are doing several things. So these are my students, and some of them already graduated. For example, Chai Mongkon already go to Germany, but he still joined the group, and we are doing a lot of different stuff. So we look for pulsar, not only dark matter. In the beginning, we did only dark matter, but now we are interested in pulsar because somehow we have to find another choice to explain. Maybe dark matter doesn't work, so we learn to understand the other nature like pulsar or supernova. And then we try to construct the gamma ray. So we use a lot of data, basically not only electron and positron, we also use the gamma ray data. And yeah, we are doing a lot of work about astroparticle physics, and we have collaborations. Soon we will try to have contribution of this work with my former supervisor in Spain, for example.
I see.
And we collaborate with people at NARIT.
Okay.
And as I explained in this Thai CTA group, we are doing something in Thai CTA group. So
I see.
please join us if you are interested. We have group meeting every Friday, very active group.
All right.
They have group meeting even I'm not there. My students are quite active.
Right. All right. So well, it seems to me like you have very big networking of collaboration, right? From like in Thailand, also from abroad as well, which is actually very good for Thai students. Well, yeah, I believe, and I believe that if anyone who are interested in like doing research in this kind of field, I think they can contact you directly, right? Or maybe send you an email or in the chat box of Facebook, possibly, I think. Right. I believe
sure. Anyway, it's fine. Email, Facebook.
You still have more room for people to get in, right? In your
we have a lot of students, but yeah, we still have some rooms if you are interested. Yeah, because
I believe there are always more rooms, right?
Yeah.
If people want to come and join your research group.
Of course, yes, we can collaborate with the other people. It's not only me. Like I send my student that worked at a postdoc in NARIT with Amel, for example.
I see.
Yeah.
Yeah. Networking is very crucial ingredient, right? Yeah, in doing research, right? Standalone is maybe not a good way on doing this, because actually I believe that you need a lot of data, right, to analyze, and you need that's why you need a very big group of people helping to analyze data, getting the data, something like that, right?
Yeah, and the one thing is we form group for some years, so my students become expert nowadays, so they can suggest the other students. So yeah, it's quite successful in my opinion.
All right, okay, good to hear that.
They make workshop by themselves and then teach the other student. For example, they are very active. I think something they even know better than me, because nowadays I don't have so much time to learn new things, but my students learn new things for me, so it's very good way.
Yeah, that's very good and very positive to our society.
Exactly, group meeting is very important. If you have to make group meeting every week, and the thing will keep going little by little.
Yeah, sure. I think that is also a basic secret ingredient, right, for doing
Yes.
research. Yeah,
Group meeting.
continuously keep going, right? Yeah, this kind of group meeting is like basic element, I believe that. I think. Okay, I think well, it's about time. So let me thanks our speaker again, Dr. Maninet Vechikama, for this very wonderful talk and discussion at the end. And thank you for the online audience to stay with us for lovely almost 1 hour, I think. Okay, before I go, please spend your time a bit on doing the survey form, which actually provide in the comment below the link. I think below the live here in the Facebook. All right, okay, and also in the YouTube as well. And see you again in if Colloquium number 4 next month. Stay tuned then. Bye. Thank you very much.
Thank you very much. Bye.